Hello, it's Mrs. Scarpel, and this video will be the first part of Unit 1, Lesson 2, the I rule lesson. So the jump start for the lesson has these three statements. When I look at a table, I recognize a linear function if. When I look at a graph, I recognize a linear function if. And when I look at an equation, I recognize a linear function if. When it comes to the table, what you should be recognizing is that the first difference is constant. Or as some students say, there is a constant rate of change. On a graph, you should recognize a linear function if the graph is a line. When it comes to an equation, you should recognize a linear function if it is written in y equals mx plus b form, so slope-intercept form. The term with the highest power has x. So you don't want any exponents on your x in your equation for it to be linear. So these are some things that were mentioned by students in class. In this lesson, we're still going to be modeling patterns with functions, and we're going to be comparing and contrasting linear and quadratic functions. So we'll be looking at how are the quadratic functions different than the linear functions. This video, part 1, is going to focus on the linear part of it. We have Marco, who has started a new blog about sports at Imagination High School that he has decided to call iSight. He created a logo for the website that looks like this: an eye made out of squares, sight. He's working on creating the logo in various sizes to be placed on different pages on the website. So he has these 4 different sizes, these 4 designs. And if we look at this, he added a square on each end, and he added 1 in the middle to get size 2. For size 3, added 1 on each end, added 1 in the middle. 4 is the same thing, added 1 on each end and 1 in the middle. So we're going to develop a mathematical model for the number of squares in the logo for size n. Now, a mathematical model can be a recursive formula, an explicit equation, a graph, or a table. I'm going to start with the table, and I'm going to list the various sizes. So we have 4 sizes. Notice my table has 5 and 6 as well. Hopefully we see a pattern that is happening that we could determine how many squares there will be in size 5 and size 6. So we start by counting size 1. We have 1, 2, 3, 4, 5, 6, 7. 7 squares. Size 2 has 1, 2, 3, 4, 5 top and bottom for a total of 10, plus 2 in the middle is 12. Size 3, 1, 2, 3, 4, 5, 6, 7, top and bottom, for a total of 14, plus 3 is 17. Size 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, top and bottom would be 18, plus the 4 in the middle is 22. Let's take a look at the first difference. So we have 7 to 12, 12 to 17, 17 to 22. The difference between 7 and 12 is a positive 5. I would add 5 to 7 to get 12. 12 to 17 is another 5. 17 to 22 is another 5. So our first difference is constant. It's always adding 5. So I'm going to add 5 to the 22, and I'm going to add 5 to that value to get size 6. So 22 plus 5 is 27. 27 plus 5 is 32. If we graph this, I'm going to put my sizes across my x-axis. And I'm going to place the number of squares vertically. And I need to be able to plot up to 32. So I am going to go with a scale of, I'm just going to go by 5s. So I'm going to mark every 10. So size 1 has 7 squares. Size 2 has 12. Size 3 has 17. Size 4 is 22. Size 5 is 27. Size 6 is 32. These points appear to lie in a line or on a line, or a line could be drawn through them. So we have this first difference is constant, we have the points showing up in a line. Those two things themselves will tell me that I have a linear function, a linear pattern. Now let's write the recursive formula. Anytime you write the recursive formula, you need to state the starting value. So size 1 has 7 squares, has a starting value of 7. Then we write f of n equals f of n minus 1. Remember that represents the previous term. And what we're doing over and over is we are adding 5. That is our recursive formula. We're always adding 5 to the previous term. The explicit equation, because this is a linear pattern, your explicit equation should represent that of a line. Well, our rate of change is always 5, so we have 5n, that's our slope with our variable we're using, but we need to determine the y-intercept. The easiest way I have found to do this is plug in the size number for n and take it times 5 and determine what we need to do to that to get our number of squares. So when I do 5 times 1, that's 5, but to get the 7 squares I need to add 2. And we can test this. 5 times 2 is 10, plus the 2 is 12. 5 times 3 is 15, plus the 2 is 17. So we have our explicit equation as well. In the next video, I'll focus on the quadratic pattern and then some review material that you will need.